So in this session, we are going to talk about performance study. So last time we had discussed how to measure the code runtime using the so-called system.nanotime, and this is going to produce the time unit in nanoseconds. So we looked at how to measure the code when it comes to the usage of array list over linked list in our last session. Um, so it's pretty important to understand how to measure the code runtime, and one could always use a long data type so as to make sure that the time can be represented using a larger number, and then you could use the time elapsed here, which would be just the end time minus start time. And any code that you want to measure the runtime would go in between the start time and end time so that the timer can effectively measure the runtime. So when it comes to measuring the runtime and producing experimental results, there are two ways to display the results. One is the tabular form, where the raw data is simply presented in a tabular structure, and it will show us the each of those entities along with the time taken. But it's pretty difficult to show the relationship between the different entity that we have in our experiment that we are trying to measure without any formula. Whereas if we use a chart form, then clearly the data is graphed, and then you could see that, like, if you have a line like this, and then you have another line, and you have the third line, so clearly you could see the relationship pretty easily by looking at the chart, while comparison with the tabular form. So there are different ways to represent the experimental result, right? So let's look at the tabular form here. Let's say that I have, let us suppose that I'm having an iterative code, and the iterative code is measured, and then the recursive code is measured here. And as we know from our earlier lessons, recursive code takes a longer time than iterative code. If you recall, the difference between recursive and iterative is faster, recursive is slower, and then iterative was recursive was elegant and easy to look like. The number of lines of the code would be lesser, but iterative could be more sophisticated, let's say, and more the number of lines would be more, right? So that's the iterative, whereas the recursive would be the number of lines would be much lesser, and it's elegant and easy to look to our eye, right? But really, when it comes to the time efficiency, iterative code, as you can see clearly all over this tabular form, that the numbers are pretty low compared to the numbers that we see in the recursive code here, right? But although that we can see this in the tabular chart, what is not so obvious is the difference, right? So how much different is it? So if you would look at this particular chart, the iterative is the flat line right here, which is all the way to the down, all the way down, and then you can see the recursive line is, like, so higher, and it's going exponential, right? So you could clearly see the difference here between iterative and recursive. After a certain point, recursive just takes off, right? And then it's going to be a little bit time taken, right? So it will be more costly when it comes to the time efficiency. Some challenges in this particular measurement of experimental running time it's difficult to compare unless we have the same hardware and software. So if we use the system.nanotime, it would produce different running time based on the hardware and software installed on our machines. So it's not stable, right? So it's not stable across platform, not stable, right? And then also it depends on the inputs that we are testing. So it really depends a lot on the inputs. One can only test so many inputs, right? But then what if we want to measure some of those inputs that we have not tested? Then this approach would not work and it will probably produce some outlier conditions. And it also asks us or forces us to implement the algorithm. It cannot guarantee any partial algorithm predictions, right? So you want the full algorithm and your full tool to be implemented. Only then we could use the system.nanotime, right? So these are the major challenges when it comes to the use of system.nanotime. But then we could try to solve these challenges. Let's say we would want to compare the efficiency of two algorithms, and let us say we would like to consider all inputs, right? And let's also say that we want to evaluate the algorithm at the algorithm level rather than at the implementation level, right? And finally, we want to compare the efficiency of two algorithms, let us say. We could also do that. If we can do that, that would be some solution to this challenges which we had outlined in the previous slide. So one method of doing that would be the so-called count primitive operations, where we will be able to count all the operations step by step manually. We break it down into primitive operations. So we have 6 primitive operation. Every time you're doing an assignment to a value to a variable, let's say int x equal to 10, that's one primitive operation. Let's say following an object reference. Let's say that you have student obj equal to new student. So that's following a object reference, right? So student is a class and obj is an object, and every time you initialize an object like that, then you're simply going to outline that as a primitive operation performing an arithmetic operation. The third one, let's say int z is equal to x plus y. That's an arithmetic operation, right? So arithmetic operation plus here takes up one primitive operation, and then equal to takes up an assignment there. So basically it takes two operations, right? It takes two operations. Comparing two numbers, let's say that you have if I less than j. If you have that comparison, then that takes up one operation, right? One primitive operation. And then accessing an array index. Let's say that you have array of 0. Let's say that you are trying to print array of 0. And array of 0 right here takes up one operation, right? So every time you're accessing an array index, that takes up one operation. And finally, if you're calling a method, let's say you're calling a method called add, and you're passing some argument, that takes up one operation, right? So every time you're calling a method add, that takes up one operation to call that method and then returning from that method. So there's a lot of calculations that one would need to do. As you could clearly see, is that these primitive operation, every time you're having an instruction, that instruction correlates to the running time of a computer, right? If you have 100 instructions, let's say I have 100 instructions, and then I have 1000 instruction on the other side. So clearly 1000 instructions takes a longer running time compared to 100 instructions, right? So clearly we are breaking it down by instructions, and we are saying that instruction correlate to the running time. We will look at few examples. Let's say that int x equal to 10. is an assignment. So it will take up one primitive operation. Int y equal to 20, it takes up the second um, primitive operation. Int z is equal to x plus y. You please look at the plus sign here. That's one operation. And then you have an equal to, which is an assignment. So that particular line would count for 2 instructions. And then you have system.out.println. Every time you have a system.out.println, that's a method as well, right? So that's a method not written by us, but it's written by Java. Let us assume that this system.out.println has a series of lines and instructions, and let's assume that it takes 5 primitive operation internally. We are going to make that assumption. We don't know how many primitive operation it takes inside the print method, simply because that's not developed by us. It comes from the Java framework, but we make that assumption as fine, right? And then you can see here, we are calling that function, right? Every time you're calling something, that's going to take one additional operation. So total of 6. We assume that print method has 5 primitive instruction inside, and then because we are calling the print method and we are returning from it, it will take one primitive operation. So that's a total of 6 for this particular line. So now we will simply add them all. So we can see that there is a total of 10 primitive operations, right? So that's 10 instructions being executed for this particular code snippet. Let's look at one more example. Let's say that this particular example, we have an assignment int sum equal to 0. That's number 1. And then here we have a print statement, right? So print statement, we are making the same assumption. 5 for the number of instruction inside the print method, and then 1 for calling the method and returning. So total would be 6. And then we need to see what's going on inside this for loop. So that's something interesting going on. We have a for loop here. How can we count the number of instructions for the for loop, right? So in order to do this, let's first write it down here. We have I equal to 0 and I less than 5. So initially, first assignment is going to be I equal to 0, right? So that's my first assignment. And then you could see that it is going to check if I is less than 5, right? So that's the second step. First is the assignment, and then second is the validation or the comparison operator, where we compare I less than 5, and then we are going to go inside and increment sum. So sum is incremented, right? So meaning sum equal to sum plus 1. So this is nothing but sum equal to sum plus 1, and thereby it counts for 1 instruction, right? And then next time I equal to I plus plus, so I would be incremented to 1. I would be checked if I less than 5, then again sum, then I equal to 2, I less than 5, sum, I equal to 3, I less than 5, and then you have sum, I equal to 4, I less than 5, and then you have sum, and then now you should see I becomes 5, I less than 5. It's not I less than 5, right? So I equal to 5 already, so it will stop right here, right? So how many instructions in total? You could see that for each of them it's going to be 3. I equal to 0, I less than 5, sum. So it's 3 times 1, 2, 3, 4, 5. So 3 times 5 is 15, plus 2 would be 17, right? So total of 17 instructions. So clearly you could see that the for loop here would have 3 such instructions in this case, because there's only 1 instruction inside. So it would have 3 such instructions for 5 times. That's the number right here. And then 2, in addition to that, we will have 2 more, right? So the total will be 17. So then if you can clean up a little bit this one here. Um, so this was 6, right? And then the total for loop, as we had counted, was 17. So then the total number of instruction will be 1 plus 17 plus 6. So which is 24, right? So approximately there are 24 instructions, or primitive instructions as we call it, by doing this counting method. But then one disadvantage of this counting is that we need to do a lot of counting, and thereby this is going to slow down a lot, right? So that's going to be a disadvantage here. Okay, and manually we need to do a lot of counting. That's what I mean. Yeah. So order of growth, right? So when it comes to assuming the data size as n, what's the order of growth? How can we measure this running time and say that, okay, so this one takes longer, this one takes lesser running time. So you have a constant factor, which is the c, then you have logarithmic, and then you have linear. Linear is just the n, then line arithmetic, which is n times log n, then you have quadratic, which is n square, cubic, n cube, and then exponential is 2 to the power n. So exponential is the most longest, or the longest running time that it would take, and constant would be the least running time, right? And then everything else would go in this cycle, like in terms of this running time. So for example, cubic would take a longer running time than quadratic, right? So n cube is clearly greater than n square, right? So you can see in this chart here, this chart clearly shows you that the constant is the lowest one right here, and then you have logarithmic, then you have a linear, then you have line arithmetic, and there is 9x plus 27, which is somewhere in between linear and line arithmetic, right? So 9x plus 27 is somewhere between, that's like saying that 9n plus 27 and then 9 log n, right? So clearly you can see that it's somewhere in between line arithmetic and the linear one, right? And then you can see the next one in that sequence would be quadratic, and then cubic, and finally you have your exponential, right? So exponential would be somewhere like this, right? So it's like way higher than any other term that is being used here. So what's the deal with recursive functions? Why does it run so slow? What is the order of growth, right? So clearly, that's going to be a thinking exercise for you here. I like everyone to think about it yourself. And then next time I will use Slack to share my thinking result. But for now, I would like everyone to think about it yourself. Why is the recursive so slow? And what order of growth does it use? Clearly, the counting method has a limitation, that is, it deals with a lot of manual steps when it comes to measuring each of those instructions. One could use a big O notation in order to avoid such a limitation. A big O notation has the input size as the x-axis and the y-axis as the running time. And you could see that we have a function here called f of n is equal to c times g of n for any n greater than equal to n naught, right? And n naught should be greater than equal to 1. You see this graph here? This is n naught, right? This is n naught right here. And n naught is greater than 1 clearly. And then after this point, the CG of n is higher than f of n, right? So till this point, f of n was higher, as you can see, and g of n was lesser. And then after a certain point, the g of n takes off, and it's going to be greater than f of n. So this is why we will call this f of n as big O of g of n, simply because we know that there is a constant that one could multiply cg of n for that f of n. Let's look at one theorem here, and then we will look at some examples to follow that as well. So let's say f of n is equal to 8n plus 5, right? And then we want to prove that it's big O of n. So simply we need to say that we need to prove that 8n plus 5 is less than equal to cn, right? And 8n plus 5, we know that was f of n. And according to the previous slide, you can see f of n is less than equal to c times g of n. Less than equal to c times g of n. And g of n is nothing but big O of n right here, right? It is n. So we need to prove that f of n was less than equal to n. And f of n is given right here. So I'm going to say 8n plus 5 is less than equal to c times n. Right? So we need to prove that. So let us simply pick one constant here. Let's say that c is equal to 9. And then you can see yourself 8n plus 5 is less than equal to 9n. And this will hold good if you start making substitution for n. Let's say n equal to 10, 20, 30, 40, and so on. If you do that substitution, so I will do that substitution for one case, n equal to 10. So if n equal to 10, 8 times 10 is 80. 80 plus 5, 85 is less than equal to 9 times 10 is 90, right? And I could do it for one more case, which is 20. So if I substitute 8 times 20 plus 5 is 165, less than equal to 9 times 20 is 180. So it's proved, right? So the theorem is proved here by doing some substitution for n value. If you increase the n value, you would find that the theorem to be proved a lot, right? It's not always that we need to substitute c as 9. You could also do c as 13, for example, right? So if you do c as 13, then simply, the proof here should be 8n plus 5 is less than equal to 13n, right? So if you do the substitution, this will work for n naught starting from equal to 1. So which means I can substitute n equal to 1. 8 plus 5 is less than equal to 13, right? And then if I substitute n as 2, then it will be 16 plus 5 is less than equal to 26, and that's proven as well, right? So we could simply choose a value for c and n naught, and we could do that substitution, right? In this case, we have chosen n naught as 10, but you could choose any value for c, and we need to prove that if it is still true, if it is still big O of n, right? Let us look at some rules here for big O notation. I like to run through these rules. First thing first is we need to ignore the constant factors, right? So for example, 3n, 6n, 0.5n, or 1 followed by several zeros and then n, they're all going to be big O of n, right? So the constant doesn't matter, right? So if you have 3n, simply take out that constant and you can call it big O of n. And then ignore the lower order terms. If you have 3n plus 6, then you can ignore 6 and you can call it big O of n. And the same thing right here. 4n cubed plus 8n minus 6, we could safely ignore 8n and 6. Why? Because it's much smaller than n cubed. And you can simply say that it's big O of n cubed, right? And the same thing right here as well. You could simply ignore the 1 followed by multiple zeros and make it big of n. Um, and then finally, use the most specific order of growth, right? So when something is big of n, it can also be technically big of n square and big of 2 to the power n for different c and n naught combination, right? So choose the tight approximation all the time, right? We need to choose the tight approximation. Let us look at two examples. Okay, so the first one is we have a double for loop here, nested for loop. If we want to measure the running time using big O notation or big O analysis, simply we ask a question. You can see that the n here is the data set size. So how many times would the outer for loop run? It's clearly going to be big O of n, right? So it's going to run big O of n number of times. And the inner for loop here has some interesting pattern. It's going to run j equal to 1. The next time it becomes 2. Next time it becomes 4, 8, 16, 32, 64, 128, 256, 512, 1024, so on and so forth. So you see how fast the rate is increasing. So every time you have the rate increasing using a multiply or a divide operator, then the runtime is going to be log n. Right? Why is it log n? Simply we are going to have the rate to be much slower than it is n. It's not linear. It's not like 1, 2, 3, 4, 5. It's not increasing in this pattern. It's increasing 1, 2, 4, 8, 16. You see? It's going to be log n because it is going to be the increase. It's going to be much smaller in this case. So the total runtime is going to be n times log n. And that's big O of n times log n, which is the line arithmetic. Again, let me repeat myself. The first for loop, outer for loop, runs linear, or it takes the n big O of n time, and the second for loop, which is taking big O of log n, and we simply need to multiply them because it's a nested for loop. So let's look at the second example. Again, we asked that question, outer for loop is going to increase by 2, 1, 3, or in this case it starts from 0, 0, 2, 4, 6, 8, but that increase is still much smaller than multiply, you see. So every time you're using a plus equal to 2 or plus 1 or plus 2 plus 3, all those are still linear because the increase is not as much as you multiply that number by 2, right? So thereby the outer for loop continues to be n. The inner for loop is going to be n as well because the increase is done by 1. And the total runtime is n times n, which is big O of n square, and it's quadratic. So this particular example is quadratic. Okay. All right. Well, let's look at one more quick example. I like to run a for loop here. Let's say int I equal to 1, I less than n, I plus plus. And then inside that for loop, let's say we have int j equal to 1, j less than n, j plus plus, and let's say we have one more for loop inside that, int k equal to 1, k less than n, k plus plus, and let's say we are doing a sum minus minus inside that third for loop. So what would be the runtime here? Clearly you can see the outer for loop runs for n number of time, the second for loop runs n number of time, third for loop runs n number of time, so it's going to be n times n times n, and thereby big O of n cubed, right? It's going to be cubic. So if you find 3 nested for loop, all of them are going to be incremented by 1, then clearly it's going to be big O of n cube, right? So let's do a small change here. Instead of k plus plus, let me make a correction. So let's say k less than n, k equal to k times 2, and then I have some minus minus. What would be the runtime in this case? Let me erase this here. Okay, so you would have given a thought by now. Think I just accidentally pressed something. Okay, so yeah. So you could see that the outer for loop runs n time, no question, because it's incremented by 1. Second for loop runs n time, but the third for loop here doesn't run n time. It's going to be log n, right? So it's going to be log n simply because the k here is incrementing by 2. So thereby it's going to be log n. And the total runtime is n squared log n, right? Big O of n squared log n. Okay, with that, we will take up this reading assignment, which is based on the Goodrich textbook, chapter 4. And if you guys have any questions, you should feel free to ask. The next time we will go back again to data structures, and we will talk about stacks and queues as the next potential topic of discussion. Okay, with that, I'm going to end this video. Thanks for watching this clip.